Welcome to this lecture on transition metal organometallic chemistry from principles to application. This is the incidentally this is the 60th lecture and the last lecture of this course, and I have decided to summarize the topic that has been taught in all the 59 lectures, so as to help us get a perspective of what has been done throughout this course. In the beginning, I have this pleasant duty of acknowledging and thanking the people who had been behind this effort, particularly in helping me in preparing for this course. To begin with, let me thank Mr. A.P. Prakasham. He is the teaching assistant for this online course, and he would be the one who would be taking exam, conducting and grading the quizzes, editing all the videos. I would also like to thank the whole of NPTEL video team at IIT Bombay, who had been extremely friendly and coached me through this video graphing of this course. And in particular, I would like to mention Mr. Tushar, Mr. Amin, Mr. Vijay and Mr. Ravi, who had always been smiling in helping me learn how to present in front of the video taking this course. So, with that, let me just start summarizing the topics that we have covered throughout this course. To begin with, we started on with the history of organometallic compounds. What we had seen that this field of organometallic chemistry is relatively new, about 200 years or slightly over that old, and the importance of organometallic chemistry can be gauged by the fact that even though it is relatively a new field, many Nobel Prizes have been awarded to recognize the importance of the field, so much so that in the last 100 years or so, about 9 Nobel Prizes have been awarded for various discoveries in the area of organometallic chemistry, and this sort of justifies the importance of this topic. Now, in the earlier classes, I have gone into the classification of organometallic compounds, particularly looking at the stability and reactivity of metal carbon bonds. These sort of started with type of overlap they make. One of the bases for classification of organometallic compounds starts with this 18 valence electron rule, and based on these 3 classes or 3 types of organometallic compounds can be made, which is class 1, class 2, class 3, and they are classified as class 1 are the ones which can have valence electron more or less than 18, from maybe can have 16 to 19, and these are called class 1 types, which does not obey 18 valence electron rules. The class 2 types are the ones that can have electrons, but should not exceed 18 valence electron, and class 3 are the ones which actually obey the valence electron rules. So, what we saw that there is so much of space for types of compound to exist beyond 18 electron rule that we are all familiar with. Now, we had also seen that the reason for bifurcation of this or division of these classes of organometallic compounds is particularly because of the delta O splitting, and these class 1 are usually shown by 3D transition metal for whom the delta O splitting is relatively small, and as a result the T2G is non-bonding and Eg star is weakly antibonding. So, Eg star is weakly antibonding, may be populated, T2G is non-bonding, and as a result can have anywhere between 12 to 22 electrons to populate with. So, they do not obey the 18 valence electron rule. For then next comes the class 2. Class 2 are for larger metals, mainly 4D and 5D transition metals, for which the T2G is essentially non-bonding and can have 0 to 6 electron, whereas Eg star is strongly antibonding and does not populate it, and this can be seen over here. Eg star is now very high in energy. As a result, this mostly remains unpopulated, and as a consequence up to 18 electrons can fit in these type 2 type complexes. Then comes class 3 types where the splitting is even the largest, and this is good for pi acceptor ligands such as carbon monoxide PF3, and here T2G becomes bonding owing to interaction with the ligand orbitals and are occupied. As a result, they are always occupied, and Eg star is strongly antibonding and remains unoccupied. So, because of these pi electrons of the ligand interacting with the pi electrons of the metal orbital, this T2G becomes strongly bonding, and that is why an Eg star becomes strongly antibonding, and as a result they do not exceed 18 electron, and hence they obey 18 electron rule. Now, with this classification of 3 types of organometallic complexes based on their molecular orbital correlation diagram, one then understands how these organometallic compounds react. Now, that was on the basis of metal orbital. Now, classifications can also be made based on the ligands, and the ligands can be the ones which are of different type. They can be sigma donor or pi acceptor, and to begin with we looked at sigma donor ligands, particularly their properties, thermodynamic stability, kinetical abilities, interaction of CH. And to start with, we looked at various sp3 hybridized like metal alkyls, the type of bridging they kind of show. We looked at sp2 type sigma donor ligands, the aryls, vinyl, acyl, and then finally to sp type, where carbine, alkylidine, alkenyl, vinylidine, so on and so forth, and type of the bridging they undergo. Now, for sigma transition metal organ complexes, one phenomenon which is very common is this phenomenon of beta elimination. Now, beta elimination is a primary mode of decomposition which sort of leads to decomposition of these complexes, and then we also looked at a discussion as to how to suppress the beta elimination, and if so one can really achieve a very stable organometallic compounds, and for that we have looked in to various strategies in place. For example, formation of olefin that will have either sterically or energetically unfavorable, which is Brett's rule, then absence of beta hydrogen, or the central atom is coordinatively saturated. If all of these are put in place, then one can well stabilize transition metal complexes. We had seen that with examples. And then we looked into main group sigma alkyls, particularly the organorhenium oxides of the type shown over here. These are important, versatile, hard Lewis acid, water soluble, stoichiometric catalytic reagents, and are used in various useful reactions like olefin oxidation, Baeyer-Villiger oxidation, olefin metathesis, olefinations of aldehydes, so on and so forth. Some of the examples we have also discussed. Now, moving on from organorhenium oxide complexes, we went to an interesting topic which is very challenging, which is and of contemporary interest, is this CH activation. The CH activation of poorly reactive alkanes by intermediately binding to transition metal can lead to subsequent functionalization and leading to utilization of fossil fuels. So, there are some holy grail transformations, for example, acetic acid from methane and carbon dioxide, methanol from methane are important goal, and we have also discussed about inter and intramolecular CH activations, of which the intermolecular CH activation is even more challenging. We have also looked at the thermodynamic criteria for CH activation to transition metal, which is unfavorable compared to hydrogen addition to transition metal, because metal carbon bonds are weaker than metal hydrogen bonds, which has a negative enthalpy of formation, whereas metal carbon has positive or almost thermoneutral, with enthalpy being 0. Now, the presence of CH activation is characterized by structural data as well as NMR data. Based on the carbon chemical shifts, one can sort of discern the extent of CH activation. Infrared values gives useful tool for looking at CH activations, and then the increased nature of the acidic CH group. So, proton and the carbon are important criteria for understanding the presence of CH activation. We have looked into several binding modes of alkanes, and what is important to note here is that alkane can bind in a varied fashion, which can be eta 1 hydrogen, it can be eta 2 hydrogen of the type shown here, it can be eta 3 hydrogens, or eta 2 carbon hydrogen, and then the agostic transition metal alkyl bond energy is around 60 kilojoules per mole, and This is just the plain sigma interaction. So, this is considerably a weaker interaction. We have looked into the binding mode of transition metal alkane with respect to being two interaction. One is the sigma interaction donating on empty metal d orbital, and the other one is the filled metal orbital donating to the sigma star, which is more of 2 electron 3 center in nature. So, this is a non-classical interaction, so we have one sigma and another pi back donation, and this is similar for various CX kind of activation, where X can be hydrogen, carbon and silicon. There is also a sigma donor pi acceptor synergism responsible for the stability of the sigma complex, and this sigma complex is followed by oxidative addition, where the coordination number as well as the oxidation state of the metal increases by 2. We have seen that. And finally, with respect to CH activation, what we had seen that there are several rearrangements that occur depending on which hydrogen is bound to the metal in a sigma fashion, and in one way, if it goes further, then it oxidatively adds this CH3 hydrogen to give the metal hydrides, and if it proceeds the other side, then it is a reductive elimination leading to metal and CH4. So, what we see that sigma complex is sort of sits in the middle between oxidative addition product as well as reactive elimination product in the reaction coordinates, and that is an interesting observation. Then after looking at CH bond activation, we have looked at C bond activations. We had seen how the CC bonds interacts with transition metals in perfluoro sigma complexes, as well as we have taken a look at sigma donor pi acceptor ligands, and in that perspective looked into alkenyl, aryl, alkanyl and transition metal carbene complexes. Now, CC activation is more difficult than hydrogen-hydrogen and CH activations, even though the hydrogen-hydrogen bond in H2 and CH bonds in alkanes are more stronger than CC bonds, but statistically the reason for this challenging activation is CH bonds outnumber CC bonds. CC bonds are sterically inaccessible, and furthermore the pre-coordination of CC bonds to transition metal becomes difficult. Now, CC bonds in transition metal alkanes, single bond remains unaffected, and ligand to metal sigma donation as well as weakens the CC bond, as well as metal to ligand pi donation cleaves the CC bond. For example, in toluene, the bond dissociation energy is 427 kilojoules per mole of CC bond, which is more stronger than benzene HCH bond dissociation energy of 368 kilojoules per mole in benzene. Now, in order to understand this bond activation, we have looked at the cyclopropane and alkene kind of systems for various CH activations as well as CC activations, and we see that there is a similarity in terms of ligand to metal sigma donation and metal to ligand pi donation. This synergism operates not only in the metallocyclopropane kind of intermediate, but also in alkenes kind of intermediate. Then moving on from CC bond activation, we have discussed transition metal perfluorocarbon complexes, for example CF3COCO4 and CH3COCO4, and what we saw that the perfluorohydrocarbon complexes are more robust. So, we have looked into various kinds of reactions which are favorable or are unique to these perfluorometal bonds. For example, CO insertion in metal carbonyl occurs readily, but in the perfluorinated organocarbonyl it does not take place. In the tune of CC and CH bond activation, CF bond activation probably is by far the most difficult to achieve, with CF bond energy between 400 to 500 kilojoules per mole, and we have looked into various catalytic cycles that are in place that undergo CF bond activation. Now, despite the fact that the CF bond activation is difficult, there are several examples we have discussed which shows CF bond activation. Moving on from that, we have moved into transition metal alkenyl and aryl complexes, and here also we have seen that sigma donor sp2 center as well as sp ones. Now, transition metal alkenyl, aryl and alkenyl complexes, they occupy position between sigma donor alkyl and sigma donor pi acceptor ligand like carbon monoxide, phosphine, RNC, etc. We have compared the reactivity of transition metal aryl versus transition metal alkyl, and then what we concluded that transition metal aryl complexes are slightly more stable than the alkyl complexes, and that is because their bond dissociation energy is only 10% higher than the methyl bonds. For example, titanium tetraphenyl decomposes above 0 degree, whereas tetramethyl decomposes as minus 40 degree. From then we have moved into transition metal alkynyl complexes. These are isoelectronic with cyanide, carbon monoxide. These acetylides are strongly basic, undergo hydrolytic cleavage, and what it sees that interaction with the metal makes the complexes more stable towards hydrolysis. Coordination of these acetylides to metal make them less reactive. Then we moved on to another important aspect, which are transition metal carbene complexes. That shows that has a metal carbon double bond. In this regard, we have covered Fischer carbene as well as Strock carbene, and then we have looked into Ardengos carbene, where by a free carbene species was isolated, stabilized and structurally characterized. We have looked into various synthetic methods that are available for preparing these carbene complexes. We have looked into type of the spin states each of the carbene signify, for example, signet and the triplet. We have looked into the interaction that occur in the singlet Fischer kind of carbene between the metal and the ligand, as shown by sigma donation and pi back donation, and the same type for the triplet Strock kind of carbene, which is a covalent bond between the metal sigma bond between the metal and the carbene orbital, as well as metal pi d pi and the carbene pz orbital. So, with that we have looked into various canonical structure feasible and the characterization of the carbene moiety. After that, we have looked into various reactivity of the Fischer and the Strock type of carbene, kind of applications of the carbene, particularly with respect to Wittig reactions, and the Tewes reagent. Tewes reagent is alternative to Wittig's reagent and carry out many reaction similar to that. And moving on from carbene, we have looked into carbine, their spin states of Fischer type doublet and the quartet of the Strock type, and the kind of interaction that goes on in the Fischer type carbine as well as in the Strock type carbine. After moving from carbine, we went to metal carbonyls. These are important compound, one of the longest known compounds. We have looked into various kind of binary carbonyls that are present for various metal, and these are mainly the late transition metal. Particularly the structures of these carbonyl complexes can be very interesting, which contain metal-metal bond or bridging carbonyl. We have looked into some of the examples as well as the type of bridging that the carbonyl display, which can be eta 1, eta 2 and eta 3. Moving on from there, we have looked into the semi bridging, which is another mode of the carbonyl complexes, and the kind of examples that symbolize it. A lot of unsymmetrical sigma pi bridging metal carbonyls with 4 or 3 electron donor side donors were also discussed, and that shows side on coordination. To understand this metal carbonyl, we have looked into the orbital diagram responsible for the carbon monoxide, and then looked into the interaction of the carbon monoxide frontier orbital with the metal d orbitals, and we had looked at various kind of carbon monoxide to metal sigma, carbon monoxide to metal pi, and metal to carbon monoxide back pi interactions. We have seen how these carbonyl metal carbonyl stretching frequency can be justified to look into the type of bonding and the type of bonding carbon monoxide display. We have done a detailed analysis of transition metal carbonyl complexes, particularly with respect to the trans effect, how the ligand, which is opposite to CO, become weakened when the electron density on the metal is pulled away toward by this pi acidic carbon monoxide ligands. We have looked into another class of compounds called carbonyl metalates. These are the anionic compounds. We have looked into carbonyl metal hydrides. These are important intermediates in many catalytic reactions, and what we have seen that metal hydrides can function as a hydridic donor or a proton donor depending on the ligand and the metal they are binding to. We have seen how the characterization of the metal hydride moiety is achieved using X-ray diffraction as well as neutron diffraction, coupling constants by NMR. With regard to utility of carbonyl metalates, we have looked into Coleman reagent similar to that of the Tewes reagent that we had seen, where a large number of organic compounds were formed from these iron carbonyl metalates. we have looked into carbonyl metal halides following the metal hydrides, and then into various kind of sigma pi donor pi acceptor ligands, particularly the olefin and alkyne complexes. The olefin complexes are important, particularly in respect to catalysis, and we have looked into the type of bonding they display. Let us say the sigma donation and the pi back donation, particularly with respect to Dewar-Chart-Duncanson model, and that can be rationalized with respect to the infrared CC stretching frequencies observed for these complexes. We have also drawn an analogy in the past discussion between the epoxide and the nickelose cyclopropane complexes, and how these two sort of match each other. We have looked at how the orbital interaction of the metal orbital with the ligand orbital takes shape in explaining the Dewar-Chart-Duncanson model. Moving on from olefin, we have looked at diolefin complexes like butadiene, and looked at how the ligand orbital interacts with various forms of metal orbital, and then we have looked mainly on the alkyne type complexes, particularly with respect to cyclo-oligomerization reactions of acetylene. Metal alkyne display a versatile mode of binding, which can be monodentate, bidentate, bidentate, tridentate, tetradentate. We have looked into how these can be characterized using X-ray as well as IR studies, and then finally what we have looked at is the various kinds of interactions that we have studied in this thing. So, overall let me just brief you as to what we have done. This course started off with this theory underlying the organometallic complexes. We have looked at what are the compounds, how they were discovered based on their reactivity over a course of 200 years or so, and then we saw that how the development of the organometallic chemistry gradually came into being with understanding of the theory that emerged alongside it, and this all started with cacodyl oxide followed by Zeise's salt, which was synthesized in 1827, but the theory of it of Dewar-Chart-Duncanson model came much later in 1950s. And then we looked into the reactivity of these transition metal organometallic compounds, and what we saw that the reactivity is dependent on two kinds of interaction, mainly ligand to metal sigma donation and metal to ligand pi book donation, and these are but common for most of the transition metal organometallic complexes, and depending on their interplay or extent of forward donation or backward donation, the structural parameters of the organometallic moiety bound to the transition metal vary. We have also looked at the characterization aspects of all these transition metal organometallic compound, particularly the characterization of the organic moiety bound to the transition metal with respect to X-ray, neutron diffraction, infrared and proton and carbon NMR spectroscopies. And what also we have seen is the application aspects of this. Now, organometallic compounds are important particularly with respect to chemical catalysis, and they form excellent catalyst for various catalytic transformations. Alongside, organometallic reagents can be extremely useful for various transformations, and we have seen that with regard to Colesman reagent, to Tebbe's reagent. So, not only on the catalytic front where these organometallic compounds are of tremendous importance, but also on the utility form stoichiometric reagent purpose, they also play a wonderful role. Now, another important aspect which to be mentioned with regard to organometallic compound is their rich bonding interaction. Now, the bonding chemistry, like particularly the interaction of the metal and the ligand, is extremely rich, diverse, versatile, and moves on from the domain of classical two-centered 2-electron bonds to non-classical 3-centered multi-centered multi-electron bonds. So that is something which is extremely challenging intellectually, particularly in academics, to understand how these multinuclear non-classical bonds are formed, what leads to the formation of them, how the ligand interact with the metal with regard to this kind of bonding. So, not only from the utility aspects, these organometallic compounds, particularly in the chemical catalysis as well as in organic synthesis as stoichiometric reagents, they are useful. Their bonding is something which is unique to these compounds, and they provide a rich area for understanding the interaction of a ligand to the metal. Now, in that pretext, like usually there is this concept that ligand always denotes electron and metal accepts, but here we have organometallic compounds which show extensive and significant metal to ligand by back donation, where the ligand accepts and metal the acidic metal gives. So, these sort of apart from this classical two center two electron bonds, we also see that kind of interactions where metal provides electron to the electron rich ligands. Now, we have also looked at Ump-Along reactivity that arises because of forward donation and backward back donation. So, apart from chemical utility, apart from this interesting bonding aspect, the another important aspect of organometallic chemistry which comes to the fore is the fact that these compounds require very ingenious way of synthesizing them. These are extremely difficult and challenging compounds which need to be prepared in the exclusion of air and moisture and stored in that environment, and that requires tremendous amount of skills in manipulating these compounds. So, from the perspective of organic synthesis or from the perspective of synthesis of these compounds, they are extremely challenging and requires extremely specialized set of skills which take a long time to develop. So, from the front of synthesis, organometallic chemistry poses a host of challenges for their preparations, and the kind of strategies that have been employed to achieve those compounds are indeed very inspirational. In this regard, it is important to note that synthesis of transition metal carbene complexes, carbine complexes are one of the most difficult ones to achieve. Similarly, one can take like the handling of the Grignard. So, lot of reagents, Grignard is also lithium alkyls are important reagents that have been developed with organometallic chemistry in the fore. Now, apart from these, another important aspect of organometallic chemistry which is of note is the reactivity of these compounds. These are extremely reactive compounds, but also can be utilized to one's benefit, and we had seen that aspect upheld in the last discussion of transition metal alkyne complexes, where we had seen that the extremely unstable cyclic alkynes like cyclohexane or benzene or benzodiene, which are difficult to stabilize by themselves, can be stabilized when they are coordinated to transition metals, and they make the transition metal alkyne complexes. So, those also mark another important aspects of transition metal chemistry, whereby one can synthesize compounds which otherwise are difficult to obtain. In that regard, I would also like to note the synthesis of the cyclobutadiene and 2- dianion stabilized by lithium. Here also 2 acetylenic moiety were dimerized to form the cyclobutadiene, and then lithium was used to reduce it to make the aromatic dianion, which was stabilized with lithium 2 lithium cations, as was discussed in the last lecture. Now, overall this has been and this still is an exciting emerging field which has a long way to go, and the field has good amount of challenges that it offers. It also provides a solution to many catalytic reactions, as has been mentioned that 8 or 9 type of 9 Nobel Prizes has been conferred for this particular area, and the reactions which has emerged from this the field of organometallic chemistry are as follows. For example, the Grignard reagents, Grignard reactions, lithium alkyls, then these hydrogenation reactions, polymerization reactions, oligomerization reactions, ring of metathesis reactions, asymmetric hydrogenation, so on, epoxidation reactions. So, very many important reactions have emerged out of these compounds that we have discussed in this last in all throughout these 59 lectures, and we are summarizing in this 60th lecture today. So, with this I want to say that this course started from principles and moved on to various applications. The course would be useful for undergraduate as well as master's degree students, as well as the people in industry, particularly working in the area of homogeneous catalysis and organometallic synthesis. They would find this course extremely useful, particularly in understanding the concepts. Also, the course will provide a basis for how the catalysts have been developed for particular reactions and how they have been used in industry. So, this would find a tremendous use in both the masters academia, master students, undergraduate students, even engineering students interested in catalysis would find this course very useful, along with the industry people, industry researchers who are carrying out research on the area of homogeneous catalysis. Now, these course has thrown out the concept, has thrown in the concepts, has also showed how the concept evolved. It has given stress on each of the classes of compounds, particularly from understanding their reactivity, particularly from understanding their bonding, and trying to particularly from exploring the various synthetic reactions which are made available for preparation of these compounds, and also took a look at the various kind of reactivity each of the compounds classes of compounds specializes in. So, with that, let me once again thank you for listening to this lecture, patiently listening to this all of this lecture, and I hope that the concept of organometallic chemistry would seem very interesting to you, and the field would be something that you would may want to pursue later on then in your career. And I would also like to once again thank the TA Mr. A.P. Prakashan, who has put sincere effort in making this course through, and also all of the IIT Bombay NPTEL video team for helping me carry out this lecture. With that, I thank you for being with me in this course, Transition Metal Organometallic Chemistry from Principles to Applications.